Okay, so today we are looking at gluconeogenesis. The most important question is, what is gluconeogenesis? So this is simply a process by which the body is producing glucose from non-carbohydrate precursors. It mainly happens when you've not eaten for some time, so there's definitely no dietary supply of glucose. The body still needs the glucose, so it can use pyruvate to convert it to glucose. So you need to know about glycolysis before you begin watching this video. Otherwise, most of the things are not going to make sense. So what exactly is happening in gluconeogenesis? So in gluconeogenesis, we are simply doing a reverse of glycolysis. So glycolysis is moving from glucose all the way up to pyruvate in 10 beautiful steps. But in gluconeogenesis, we are starting from pyruvate, going back to glucose. And this is the reason why gluconeogenesis is a very simple and straightforward pathway, especially if you completely understand glycolysis. Because all the 10 steps of glycolysis are involved. But we are going to focus on step 1, 3, and 10 for the purposes of gluconeogenesis. But why are we picking step 1, 3, and 10? Now, this is very simple. All the reactions here are reversible reactions except for step 1, 3, and 10. So when we are moving from pyruvate to glucose, we literally have to go back in reverse for all the reversible reactions. But for the 3 steps which are irreversible, we need some kind of a bypass. We need some alternative. We need some alternative route. So in glycolysis, step 1 is catalyzed by hexokinase. Step 3 is catalyzed by PFK1, and step 10 is catalyzed by pyruvate kinase. Now, in gluconeogenesis, what I just want you to focus on is just the 3 steps, 10, 3, and 1. And just know the alternative enzymes, apart from these that you know from glycolysis, because we're not going to use these enzymes. These steps are irreversible. So basically, gluconeogenesis is probably 3 or 4 different steps that you really need to know. The rest are simply a reverse of glycolysis. And that's why I said it is important for you to know glycolysis before looking at gluconeogenesis. So let's begin. How is pyruvate going to be converted back to glucose? Very simple. Now, the first step involves the conversion of pyruvate to oxaloacetate by pyruvate carboxylase. Now, I want you to pause a bit. There's something you need to know about this reaction. We know that gluconeogenesis is happening in the cytosol, but this reaction, pyruvate to oxaloacetate, is not taking place in the cytosol because pyruvate carboxylase is found in the mitochondria. So I want you to know this. Before pyruvate is converted to oxaloacetate, it actually has to go into the mitochondria, where it is converted to oxaloacetate by pyruvate carboxylase. Now, the interesting part about this route is that once oxaloacetate is produced in the mitochondria, it cannot cross back into the cytosol because it has no transporter that can bring it back into the cytosol to continue in the pathway. So there is another reaction that happens right here in the mitochondria, which is simply a reversible reaction of oxaloacetate to malate, which you know of in the TCA cycle. So oxaloacetate is strategically converted to malate in the mitochondria because we just want a way of bringing it back in the cytosol, because malate has transporters that can actually make it move from mitochondria into the cytosol. So once malate gets to the cytosol, it's converted back to oxaloacetate. So please, when you look at this step, just know that it's not a direct step in the cytosol. No. Pyruvate has to come into the mitochondria, be converted to oxaloacetate via the enzyme pyruvate carboxylase, and then oxaloacetate to malate, simply for transport purposes, because we know once malate gets there, it can easily be converted back to its isomer, which is oxaloacetate. Now, once oxaloacetate is formed, the next enzyme that you just have to know of is phosphoenolpyruvate carboxykinase, which converts oxaloacetate to phosphoenolpyruvate. So after knowing this information, from step 9 all the way up to step 3 is simply the reverse of glycolysis. So you basically don't have to learn anything new if you know glycolysis. We only have a challenge when we come to step 3. Step 3 is the conversion of fructose 1,6-bisphosphate to fructose 6-phosphate. And we know that in glycolysis it's this way. So it's fructose 6-phosphate to fructose 1,6-bisphosphate in glycolysis, but in gluconeogenesis we are going back this direction. And the enzyme is fructose 1,6-bisphosphatase. So what this enzyme does is simply chopping off one phosphate group from this fructose 1,6-bisphosphate to make it fructose 6-phosphate. Then again, you skip step 2 because it's simply the reverse reaction, and you go to step 1, which also needs an alternative enzyme. So the conversion of glucose 6-phosphate to glucose is catalyzed by glucose 6-phosphatase. So basically, these are the steps of gluconeogenesis. Just 1, 2, 3, and 4. So you're basically moving from pyruvate back to glucose. Now, in the next lecture, we shall be looking at regulation of gluconeogenesis.